All right, next multiple choice section. So we did the first 30 multiple choice. Those are typically the quicker ones. You got to do a little bit of looking up something on the reference table, or it's more of a definition question. Do you remember off the top of your head? These part two questions now. The second section of multiple choice, they're a little bit different. They're typically a little bit more involved. You have to maybe do a little bit of math. You'll have some diagrams or charts like this, something a little bit extra. You got to use your reference table a little bit more, but still multiple choice. We're still going to use the same kind of strategies. Try to eliminate as many choices as we can and see what's going to make sense. 31. What is the net charge of a monatomic ion that has 15 protons, 16 neutrons, and 18 electrons? Net charge means overall charge. We know it's a monatomic ion, so it's just one atom that gained or lost electrons, something changed about it, give it a charge, and it tells us how many protons, how many neutrons, and how many electrons. You got to remember what gives things charges. There's way too many of you seem to not remember what protons, neutrons, electrons charges are. Protons are positive charge, P for proton, P for positive. Neutrons are neutral, so it has a zero charge, and electrons don't really have any memory trick I've ever heard like that. They're just the other guy. They're going to be negatively charged. So we know we've got 15 protons, so 15 plus charges. Neutrons don't have any contribution of charge, they don't have a charge, and electrons are 18 of the negative. So for net charge, we just want to see who has more of their charge. There are more of the negative charges. There's 18 compared to 15, minus versus plus. So we're going to have a negative charge on some number. I'm going to cross off my positive options because that's not going to be the winner here. The negatives are winning. How much are they winning by? There are 3 more negative charges than there are positive charges. So it's going to be a 3 minus charge overall. If you want to draw 15 little plus signs out and line them up next to 18 little minus signs, you would see that there are 3 unpaired minus signs that are winning. And that's your charge right there. 32. Table below shows the atomic masses and natural abundances of the 2 naturally occurring isotopes of rhenium, whatever. It's just some element they chose. Thankfully, there's only two versions of it they gave us. Remember, isotopes are different versions of the same element. It's 2 different types of rhenium. This one weighs 185. This one weighs 187. That's why when you look it up in the periodic table, the mass that you see there, the atomic mass, is a decimal because it's an average of these 2 versions. But they're not equally accounted for. We can see that this version, the 187 part, that's technically 186.96. It's not exactly 187. That accounts for almost 63% of all the rhenium in the universe. And the other version that weighs 185, technically 184.95, that weighs a little over 37%. So they're definitely not in the same abundance. They're definitely not as common as each other. That's okay. We want to figure out how could we figure out the average of these things. Which numerical setup shows how to do this? So how would we get the average of these things? The formula for this is the only one not on the reference table for some reason. Is always the mass of type 1 times the percentage of type 1. So what's the mass of this one version times the percentage of it, plus the mass of type 2 times the percentage of type 2, so the mass of this version times the percentage it counts for, and you can add those two numbers up and divide the whole thing by 100. Or you take the mass and kind of build in the divided by 100 first by moving your decimal point 2 spaces to the left. That's the same as dividing it by 100. Same thing here. You move your decimal point 2 spaces to the left. So now you're going to find an option where it would be 184.95 times 0.3740. And then 186.96 times 0.6260. And let's see which answer looks like that. That's this option right here, choice 2. If you were doing the math for yourself, you could multiply these two numbers plus multiply these two numbers and then divide the whole thing by 100. In this setup, they just cut right to the chase, and they divided these numbers by 100 first to make it a decimal, and then multiply them out. 33. Which general trend is observed as the elements in period 2 are considered from left to right? So let's go to our reference table. Our periodic table is going to show us what period 2 looks like. Period 2 is row 2. Remember, it says this word period right here. That means these numbers down the left-hand side. So period 2 is this row across. It's Li and Be. And on the other side, we see B, C, N, O, F, and Ne. So what pattern, what trend do we see from left to right? A lot of times you'll hear it described as in order of increasing atomic number. It just means from left to right across that row. Do we see atomic mass decreasing? Well, let's see. Atomic mass of lithium is about 7. This is 9. That's not decreasing. And then we see, what, 11, 12, 14. Okay, mass is definitely not decreasing left to right. That's not going to be our correct answer. Melting point increasing. Electronegativity increasing. First ionization energy decreasing. Well, we'd have to actually look these up. So we go to the next page in the table. You've got that nice double page spread. And all these things are on here. We have melting point. We've got electronegativity. We've got first ionization energy. All the things this question is asking for, we could figure it out. But I don't really want to look at all these things. Thankfully, it's period 2, so I can actually fit them on the page right here. I'm going to move my thing up right there, and we're going to see how the melting point looks for things in period 2, which, remember, it was lithium, beryllium, boron, and so on. So I'm going to look at, maybe I can fit elements 3, 4, 5, and 6 even just on the screen. Let's see how the melting point looks. Does the melting point increase for elements 3, 4, 5, and 6? Let's see, elements 3, 4, 5, and 6. Well, it looks like the melting point increases somewhat overall, but then it actually ends up going back down again. So that's probably not going to look too good for our answer. Electronegativity increases. Let's see, electronegativity. 1 to 1.6 to 2 to 2. Yep, electronegativity is definitely going up. That so far looks like a pretty good answer. Ionization energy decreases. Let's see, does ionization energy decrease? It's going down, but then at the end it goes all the way back up again. So that's not going to be too good. Electronegativity is going to be the one that increases from left to right, definitely. That's going to be our best option. The other two show a little bit of a pattern, but then it kind of just shoots off the other direction. Electronegativity is always going to increase, period 2, from left to right. And in general, from left to right increases in a row. Which formula represents chromium 3 oxide? Remember, the name tells you how to do this. Metal in these molecules never changes. You keep the metal name exactly the same. So chromium 3 just means a type of chromium metal. Oxide, the second element, if it's a nonmetal, you change the ending to IDE. So oxide just means a pair of oxygen, as you can see here. Every choice we have is Cr with O. It's just how many of each one do we have. So chromium, Roman numeral 3, means element chromium with a +3 charge is going to be paired up with oxygen. We need to look at what the charge of oxygen is. You go back to your reference table, and we see the charge that oxygen forms is a -2. Oxygen can be a -2 ion. So when this molecule, whatever it is, was going together, chromium with a +3 charge paired up with an oxygen with a -2. These ions are going to go together. We're going to figure out what kind of ratio they have. So I'm going to write Cr and O. We're going to figure out which number is going to go in which place. We're going to do the crisscross. The +3 charge of chromium, we bring that down and make it the quantity of oxygens we need in the molecule. And the 2, because it was a -2 on the charge of the oxygen ion, we bring that number down without the minus sign, and we make it the quantity of chromiums we need in the ion, in the molecule. We see, can we reduce 2 and 3? We can't. It's as simple and reduce as we can make it. So Cr2O3 is our correct answer, and that's choice 3 right there. The Roman numeral tells you the type of ion the chromium formed. Oxygen only has one version, so you do your crisscross as this type of ratio. Number 35. Given the balanced equation representing a reaction tells us we've got 2 KClO3s plus energy, and that's going to seemingly break apart to 2 KCl's and 3 of O2. It says, what is the mass of KCl produced, so mass of this stuff made, when 24.51 grams of KClO3 reacts completely to produce 9.6 grams of O2. This looks like such a tougher question than it is, and thankfully, this type of question has been on here a couple of years in a row, so I'm hoping you get one like this again, because this is such an easy question if you realize what you're looking at. You may be looking at saying, how am I supposed to do this math? I don't know what to do here. What kind of formula? I have the same reaction when I see these questions, because I'm expecting it to be much more difficult than it is. So much easier. You react 24.51 grams of KClO3. 24.51 grams of this stuff to begin with. And then it's going to break apart, and it says you're making 9.60 grams of oxygen. It wants to know how many grams of KCl are also made. You know how heavy the thing is to start with. It's breaking into 2 parts. If you know one of the things it breaks up into is 9.6 grams, how much of this is going to be the remainder? Just do 24.51 minus 9.60, and that's going to tell you how much of this is left over. 24 0.51 minus 9.60. And looking at my paper here, it looks like that's going to come out to 14.91. That's how much of this stuff you have, 14.91 grams. You can't lose or gain anything. So if you start with this and you make this much of O2, the other weight that you lost from here have to be in here. It's got to be the KCl. That's going to be the 14.91. 36. Which equation represents conservation of atoms? This is another pretty straightforward question. Conservation of atoms just means you can't gain or lose anything. Whatever you start with is what you need to end up with. You have to have a balanced equation. All you need to do to answer this question is go choice by choice and see which one is actually balanced. I'm going to go element by element. In choice 1, it looks like I've got one of the TIs, titanium, on the left of the arrow. At the end of the reaction, I also have one TI. So far, so good. I have 2 oxygens on the left. On the left side, I have 2 times 3 is 6 oxygens. Well, that's way too many oxygens. Where do those extra oxygens come from? That is not balanced. Doesn't make any sense. Choice 2. 1 Ti on the left, 1 Ti on the right. Good. 2 oxygens on the left. 2 times 3 is 6 oxygens on the right. Once again, does not make any sense. Where those extra oxygens come from? Choice 3. 3 TIs on the left, 3 TIs on the right. Okay, good. 3 times 2 is 6 oxygens. 2 times 3 is 6 oxygens. That's good. 2 ALs on the left. 2 times 2 is 4 ALs on the right. Nope, doesn't add up. Let's hope this one does. 3 titaniums on the left. 3 titaniums on the right. 3 times 2 is 6 oxygens on the left. 2 times 3 is 6 oxygens on the right. All right. 4 ALs on the left. 2 times 2 is 4 ALs on the right. Everything's accounted for. Everything makes sense. The pieces just switched around a little bit. This is a single replacement reaction. Everything just swapped places, but all the atoms are there. You didn't gain any extra atoms. You didn't lose any atoms along the way. Number 37. 1 mole of bromine gas has a mass of what? All you need to know is how heavy 1 mole of this stuff is. If you really want to set it up, you've got that mole equation. Moles equals grams over gram formula mass. You know you want 1 mole over here. Gram formula mass is how heavy Br2 is. You can look it up on your periodic table, and it would just be 1 times that. So really the question is asking, what is the gram formula mass of Br2? How heavy is Br2? Br2, Br2. We want to see how heavy bromine 2 is. We need to go to the reference table. Let's look up bromine is. It says 79.9. If you rounded that to 80, 2 of something that weighs 80 would be 160. Well, none of the choices here say 160, but 159.8 is pretty close. For some reason, they didn't round it off. They treated bromine as exactly as it says, 79.9. And if you do 79.9 times 2, this is the answer you're going to get. Each bromine weighs 79.9 units, and 2 of them will weigh 79.9 times 2, and that is your option 4 right there. 38. Given the equation representing a reaction, 2 NaCl, so 2 salts, breaking it down, it looks like, into 2 NAs and Cl2 also. So you had this molecule where it broke into 2 parts. What type of reaction does this equation represent? You just got to remember what the reactions are. You learned about, well, 4 of these things. Synthesis is when you're putting things together. That's not what's going on here. Decomposition is when you're breaking them apart. That's exactly what's going on here. That's going to be our answer. A single replacement reaction is like the one we looked up here, where AL is by itself, TI and O are together, and then AL seems to have moved in and kicked out TI, so now TI is by itself, AL and O are paired up. That would be a single replacement reaction, but that's not what this shows. Double replacement is if you have something like this. A, B, and C, D, and then everybody changes dance partners, so instead you now get AD and CB together. Everybody switches who they're paired up with. That's double replacement. Once again, that's not what's going on here. So it's NaCl breaking apart into 2 pieces. That's decomposition. As we start page 6, let's take a word from our sponsor. Tonight we're sponsored by Snapple Rain because that's what I bought before. Made from agave cactus, apparently. If you ever want to drink something that would hurt you if you tried to drink it in real life, because why not go for agave cactus? I don't know what it tastes like. I forget. It's weird, but it's not terrible. Number 39. Which statement describes the charge and radius of the magnesium ion formed when a magnesium atom loses 2 electrons? A couple of ways to answer this. Each choice says either Mg ion is positive or Mg ion is negative. Each choice also says either radius is larger in the ion than in the atom, or radius is smaller in the ion than in the atom. You have to remember what an ion is. An ion is when you gain or lose electrons. So let's see what happens with Mg. We need to know this information. We need to give ourselves the best chance to answer the question. Let's go look for some information. Mg. Mg makes a +2 charge, it tells us on the periodic table. If it's making a +2 charge, that means it's going to lose electrons. To go from Mg with no charge to Mg with a +2 charge, it had to have lost 2 electrons to get more positive. So it's going to have a positive charge. We see that in the periodic table. I'm going to cross off anything that says Mg ion is negative because it is clearly not. It told us it's not. I'm down to 2 choices. Even if I have to guess what the size of the thing is, I'm now guessing 1 out of 2 instead of 1 out of 4. How did it get to be a positive charge? It lost 2 electrons. Well, where do the electrons come from? If it's losing 2 electrons, it's going to be those 2 electrons right there. These valence electrons, the last 2 in its outer ring, they're going to be the ones that go bye-bye. So it had 1, 2, 3 rings of electrons. Now it loses those 2. The entire third ring is now going to be gone. I'm just going to put my pen over that third ring. Instead of being 2 electrons in the first ring, 8 electrons in the second ring, 2 electrons in the third, you're going to get rid of those 2 electrons in the third ring, and now you only have 2 rings left. So when you knock that outer ring off, the whole thing is going to shrink down. Metal ions will be smaller than what they start as because you're ripping the electrons off the outside. It's like peeling an onion or something like that. You're making it smaller. So it's a positive charge and it's a smaller radius. I'm going to cross off anything that says larger radius. And now we're down to option 3. An oxide ion, oxygen with a -2 charge, just oxygen that gained 2 electrons, has the same electron configuration as an atom of which noble gas. Well, again, we have to know what this thing looks like. What does oxygen look like when it gains 2 electrons? It talks about electron configuration. So we need to know what its electron configuration actually is. So I'm going to go look up what oxygen normally is. Oxygen's electron configuration, it says 2-6. Oxygen normally has 2 electrons in the first ring, 6 electrons in the second ring. So oxygen normally looks like this, 2-6. Except now it's oxygen with a -2 charge. So if it picks up 2 extra electrons to make it -2, we have to add 2 electrons to this. So they're going to go in the outer ring, and instead of 2-6, it's now going to be 2-8. That's what this stuff is going to look like. 2 electrons in the first ring, 8 electrons in the second ring. It's asking which noble gas looks just like this. Back to our periodic table. Noble gases are all the way on the right, and let's see which noble gas has an electron configuration at the bottom of 2-8 only. And there we go right there. It's neon. Atoms always gain or lose electrons to become ions that make them look like the closest noble gas nearby. Oxygen will gain 2 electrons to basically look like the thing 2 spots to its right. Nonmetals will end up looking like the noble gas closest to them at the end, whereas metals will lose electrons to kind of backtrack and look like the previous noble gas on the previous row. So oxygen, as we saw, is going to look like neon when it gains 2 electrons. What is the vapor pressure of propanone at 45 degrees Celsius? Anytime you see any mention of vapor pressure, go right to one reference table, I should say, and that's going to be table H. Table H is where vapor pressure is listed. It's probably the only mention you ever saw of this all year. Maybe talked about this for about a day with your teachers. Table H is the little remembered one that no one remembers is there. Here is table H. So it's just like these solubility curves. It gives temperature at the bottom. You go up to the line, and then you just read over the right to the left side, where it tells you the vapor pressure, how strongly is the liquid turning into a gas and pushing up to into the gas phase. As what is the vapor pressure of propanone at 45 degrees Celsius? So we got to find our propanone line. That's just this line right here. They don't have any kind of weird lines. They all just go in nice kind of spaced out ways, evenly spread from each other. And it's at 45 degrees. So it looks like this scale on the bottom is by 5. We got 25, 30, 35, 40, 45, 50. It is. So it asked about 45 degrees Celsius. So that's going to be this spot right here on our chart. I'm going to go up to the propanone line, which was my first one. I'm going to follow it right up and right there. It looks like it's right on a cross line, so I'm going to move over, and that's going to be going by 10, so 50, 60, 70, 80, 90, 100. The second line above 50 is going to be 70. So it should be 70 with the unit of kilopascals. Let's see if that's an option. Right there. Easy enough. Based on table G, let me zoom out a little bit with this camera. Based on table G, so let's go to table G. It's telling you which reference table to go to, just may as well turn to table G. Here we go. Here's table G, solubility curves, I was just mentioning a second ago. Based on table G, what is the mass of KCl that must be dissolved in 200 grams of water at 10 degrees to make a saturated solution? Every line and every point on every line on table G represents a saturated solution. It's telling you at some temperature, this is the exact amount that should be dissolved. So everything on here is a saturated solution. The trick of this question, it says in 200 grams of water. The standard way to measure stuff on here is in 100 grams of water. So you can't look up 200 grams or 300 grams of water. You can find how much will dissolve in 100 grams of water and then multiply that by 2 to see how much would dissolve in 200 grams of water. So let's do that. Let's see the KCl line and how much we should be able to get dissolved at 10 degrees, and then we'll multiply that by 2 to tell us how much of it would dissolve in 200 grams of water instead of the normal standard of 100 grams of water. KCl. Let's find KCl right here. Here's our KCl line. It's that line right there. And the question asked about KCl at 10 degrees. So I'm going to find the KCl line, and I'm going to see at 10 degrees, how much should I get dissolved? So there's KCl. There's 10 degrees. At 10 degrees, I go up. And it looks like I should get right about 30 grams that can dissolve per 100 grams of water. If we're using twice as much water, 200 grams, we should be able to get twice as much of this dissolved. So it should be 60 grams of KCl that can dissolve. And if I go back to my question, that's exactly what choice 3 says, 60 grams. Based on table I, let's turn to table I. Here's table I. It's a whole list of reactions. It tells you all these different reactions. Just be careful when you're reading because a lot of them look pretty similar to each other. There's some subtle differences. You may look at the wrong one. And then it gives the delta H, the change in energy. That's also the enthalpy or heat of reaction. It's telling you how does the energy change. If it's a positive number, which a lot of these are not, but if it's something like this with a positive number, it means you gained that much energy to make the reaction take place. It's endothermic. Most of them are minus numbers. Negative numbers mean you lost that much energy. So it means exothermic. So we can look at that kind of information. Based on table I, which chemical reaction represents a chemical equation rather, represents a reaction with a heat of reaction that indicates a net release of energy. Which of these numbers would mean energy is being released? Energy being released means it's going down, you're losing that much energy, you're looking for a negative number. That's all this is asking you. You got to look up these 4 reactions on here somewhere and see what the number, the change in energy says. The correct answer will have a negative number. I looked it up already. When I went through this reaction right here, the energy change was plus 182.6. Not a negative number, not the right answer. Second one, energy change was plus 66.4. Not a negative number, not the right answer. Third one, energy change was minus 84. I'm going to leave that, but it sure looks like it's our right answer. Number 4, the energy change was plus 52.4. Not a negative number, not our correct answer. 3 is the only one that makes sense. Another question where even if you weren't quite sure how to answer it says table I, it talks about the heat of reaction. It tells you how to do this. It tells you what you're looking at here. If you're looking at the energies for these 4 reactions, just see what the numbers look like. 3 of them were positive numbers. 1 of them was a negative number. That's the odd man out. Real good chance that's going to be the correct answer. And it was. Number 44. Greatest increase in entropy occurs when a 1 gram sample of water changes from what to what? Entropy is randomness. So which of these changes in the state of matter of water would increase the randomness, the disorder, the sloppiness, the messiness the most? Solid to liquid. That definitely is increasing entropy. It's getting more random. It's getting more spread out. If molecules go from being a solid, kind of packed in tightly like this, to being a liquid, where they're more spread out, a little bit looser packed like that. So that could work. Let's go on to the next. Solid to gas. Well, that also is going to be more spread out. It's also going to get more random. Again, it's going to go from solid, but now the gas molecules are kind of all over the place. So that's going to be a greater increase in entropy. I want to cross off this first one because even just between these two, this one is currently in the lead. This one's going to be more of an increase in entropy. Gas to liquid. You're moving from things really far spread out to now being a little bit less spread out. So that's not going to be an increase in entropy. That's going to go the wrong direction. That's not going to be our answer. Liquid to solid, same thing. Liquid, they're spread out a little bit. If it's going back to a solid, they're packing themselves in tighter. They're not increasing entropy. That's not going to be an answer that works. So of our four choices, solid to gas is going to increase the randomness, the disorder, the messiness the most. Entropy is going to increase the most in that type of change. Number 45. Which particle diagram represents one substance only? In these pictures, which one represents one substance only? Now, it doesn't say all the same element, it just says one substance. So that means everything in this box has to be the same as everything else in the box. So go through each box and see, do you only have the same type of stuff? Here I see four little things, and each molecule is two non-colored in circles. This molecule is the same as this, is the same as this, is the same as this. So that seems like it probably makes sense. In this one, we've got two uncolored with a colored, one colored, one non-colored, one colored, one non-colored, two non-colors, one colored. So this molecule is different from that molecule. These two are the same, and these two are the same, but they're not all the same as each other. So this is not a substance. It's not just one substance. This box below it, same idea. We've got uncolored circles and we've got colored in circles. They're not all the same thing. That's not going to be all one type of substance. Same thing over here. We've got a pair of uncolored circles. We've got a pair of colored circles. These are not all exactly the same thing, so that's not going to be our answer. This has four of the exact same thing. Each one of these things is the same little uncolored pair. That's the one that's going to be one substance only. That's our answer. I saw a couple of questions like this in the last 2 years or so on these tests I've done recently, so another common type question. Number 46, almost done. Based on table J, let's go to table J. Right here, very convenient. Based on table J, atoms of which metal will lose electrons to calcium atoms? Ions, sorry. Which will lose electrons to calcium ions. You got to think about this for a second. If one of these metals is going to lose electrons and give those electrons to calcium, losing electrons means something's happening. Losing electrons means it's being oxidized. So this is saying which metal will be oxidized instead of calcium. Which of these four metals, when reacting with calcium, will be the one that gets oxidized? And it's telling you based on table J. If we're looking at metals on table J, we know calcium is one of them, and one of these four metals will be the other guy. If one of these four is going to be the one that gets oxidized instead of calcium, it has to be higher up on table J than calcium. Calcium is right here. We need to see which of these four metals is going to be higher up on table J. So we're only looking at these four right there. Which of these four is going to be higher up and be the one that gets oxidized? Is aluminum higher than Ca? Let's see. Nope, aluminum is right down there. Aluminum is not higher than Ca. Is lead, Pb, higher than Ca? I do not see Pb anywhere down here, up there, and if I scroll down, there's Pb right there. Pb is definitely not higher than Ca. Is nickel, Ni, higher than Ca? Let's see. There's Ca. I don't see Ni anywhere, and Ni is actually all the way down there. That's not higher than Ca. Potassium, K. Well, potassium's right at the top. Potassium is higher than Ca. That's the one that, if it was reacting with calcium, would be able to be oxidized because it gets more higher priority. It is more active. It gets to be oxidized. Ca, in turn, would be the one that gets reduced. Another question where if you don't remember exactly how this works, which one has to be higher, which one has to be lower, the question tells you, go to look on table J. And it tells you calcium is one of the things involved. Just look for these other four metals and see where they are. If you know calcium is one of the things you care about, and we have aluminum, we have nickel, we have lead, well, three of the four options are below calcium, and only, potassium all the way up here is above calcium. The one that doesn't look like the other three choices, that's going to be your correct answer, because you can only have one answer. So potassium, however you solve it, is the one that will be oxidized, and calcium will get reduced. 47. Which aqueous solution is the best conductor of an electrical current? Which one's going to conduct electricity better? It's telling you one of these things will, and let's just look at our choices. Each one of the choices is NaNO3. So you don't have to figure out which type of molecule conducts electricity or anything. It's NaNO3 in each example. The only difference between them is how strong the solution is. 0.1 molar, 0.2 molar, 0.001 molar, 0.002 molar. So you have really smaller numbers and a little bit bigger numbers. Which is going to conduct electricity, electrical current better? The more stuff that's dissolved in a solution, the better it'll be at conducting something, conducting charge, conducting heat. So we want to get the biggest number, the most concentrated, and the biggest number in this case is going to be 0.2 molar. 0.2 is bigger than 0.1. 0.2 is definitely a bigger number than 0.01, 0.02. That's the biggest number. That's going to conduct electricity better. 48. Given the equation representing a reaction, we've got this equation right here. This equation represents what? Sublimation, condensation, fission, or fusion. Well, sublimation is something going from a solid to a gas, skipping liquid phase. I don't see any mention here of states of matter, solid gas. That doesn't seem like it's going to make sense. Condensation is gas going back to a liquid. That's not making sense. Once again, we have no mention of states of matter. I've got two H's. It looks like they're combining to make He, and then kick off a neutron. Well, two things combining is that can be fission or fusion. Fission is when things break apart. Fusion is when they merge. So this is going to be an example of fusion because you're combining two of the H's to get He, and then you lose a little neutron as a byproduct of that. So that's how fusion will work. Very last page of your multiple choice. Last two questions, they're bigger questions. We got a bunch of these organic structures here. Let's see how it looks. Which formula represents 2-butene? Organic compounds, the names always tell you how to draw the thing. Everything you need to know is in this name, and then you just got to see which picture matches. Look for the name. Bute. What's the prefix? Bute means 4 carbons. You don't have to memorize this because all of your organic stuff is on page 7 in your reference tables. Bute as a prefix right there on table P, it tells you 4 carbons. I now know my picture is going to have 4 carbons. The ending of the name, the -ene suffix. Let's go check the other chart. At the bottom here, we've got some names that end in -ane, some names end in -ene, some names end in -ime. This one says -ene. I'm going to look at the picture. That has a double bond. So I know I'm going to have a double bond. I'm going to have 4 carbons. And the number tells me where the double bond actually is. So there's going to be a double bond coming from carbon number 2. Let's see if we can eliminate any choices. As long as we know it's 4 carbons, let's see if we can eliminate them. 1, 2, 3, 4 carbons. 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 So the number of carbons didn't help us any. How about the fact that it needs a double bond? I see a double bond here, so that's okay. Oh, I see a triple bond in this choice. That's not going to be correct. Get rid of choice 3. Choice 2, 1, 2 bond. Okay, 1, 2, 3 triple bond right there. Once again, not going to make sense. Now we're down to only 2 choices. We're looking at choice 1 and choice 2. They look like they're almost the same thing. Each one has 4 carbons. Each one has a double bond somewhere. It's just where is the double bond? The number 2 right there means it's coming off carbon number 2. Remember, we count in each direction to see which number is lowest. In this one, counting from the left, it would be starting off of carbon number 1. And from the right, it would be 1, 2, 3 that it's attached to. So we'd call this carbon number 1. In this molecule, it's 1, 2 from the left, 1, 2 from the right. Either way, it's always carbon number 2. This is what 2-butene looks like. If you want to draw this for yourself and then just match the picture, again, bute means 4 carbons. Just draw yourself 4 carbons. -ene means there's a double bond. Do a double bond connecting 2 of the carbons. Which 2? The number 2 tells us we're going to start on carbon number 2 and go to the next guy. So carbon number 1, 2. I'm going to draw a double bond connect to the next carbon. Give the rest single bonds, and then just make sure each carbon gets 4 bonds total. This guy has 1, 2, 3, gets 4. This carbon has 1, 2, 3 already. I'll just give him a 4th one up top. This one has 1, 2, 3 already. I'll give him the 4th one up top. This one only gets 1 carbon, 1 bond, so he's got 2, 3, 4 right there. That's going to match this picture right here. I didn't draw my H's, but that's our molecule. Last question in this section. Given a formula representing a compound, and we've got this little molecule right here in the picture, which formula represents an isomer of the compound? Another really common question. Do you know what isomer means? Isomer sounds a lot like isotope. Isotope is when it's the same element, but different number of neutrons. It's very similar. Isomer means something kind of close to that. It's got all the same parts, meaning the same number and type of atoms, but different shapes or different arrangements. So I gave the example in class if I gave someone a box of Legos and didn't tell them what they're supposed to build with it. I could give the entire class the same kit and they'd probably all come up with 22, 23 different versions of the same stuff. I'm not giving you rules. We have to do the same parts in different order. So I'm going to see what my parts actually are. I've got 1, 2, 3 carbons up here. Looks like I've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And I see one little oxygen. So I need my picture to have 3 carbons, 8 hydrogens, and oxygen, but not look like this. It can't look like this or it's just the same molecule. It's got to be a different arrangement of these things. Let's just go through and see if can we eliminate anything. 1, 2, 3 carbons looks okay. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 1 oxygen. Okay, so this looks like it might work. Let's just double check the other ones. 1, 2, 3 carbons. So far, so good. 1, 2, 3, 4, 5, 6. Oh, it doesn't have enough hydrogens. This one's not going to work. It should have 8 hydrogens, only has 6. Down here, 1, 2, 3 carbons. Okay. 1, 2, 3, 4, 5, 6 does not have enough hydrogens. And also it has 2 oxygens. It should only have 1 oxygen. That's not going to work. Choice 4. 1, 2, 3 carbons. That's okay. 1, 2, 3, 4, 5, 6 hydrogens. Again, it's not going to make any sense. It does have an oxygen, but it does not have enough H's. We don't even have to worry about that first molecule. That's the only choice that makes sense. But this is an isomer because it has the same number of things. 1, 2, 3 carbons, 2, 4, 6, 8 hydrogens, and 1 oxygen. It's got all the same pieces, but it's rearranged differently. You rearrange the pieces here, it looks different down here. All the pieces are there, but they're in different places. That is what an isomer should look like. It's got to look different from this with the same stuff. All right, that is part 1 and part 2, or however you want to describe it, parts A1 and B1, whatever it is. Those are your first 50 questions. Those are all the multiple choice questions. I'm going to stop this here, and tomorrow I will record parts B2 and C1, whatever you want to call them. It's all the short answers, and we'll see how the next half of the test goes.